Hi 242. So in this video we are going to continue our discussion of antiderivatives, but we're going to discuss notation that we use specifically for finding antiderivatives, because in the previous videos you noticed that if we wanted to find an antiderivative, we just had to say find the antiderivative and write it in words or say it or something. So what we like to do is use some very special notation that says or instructs us to find an antiderivative. So let's just jump into the notation and I'll explain all the parts to you. So we use what's called an integral sign, and it's a stretched out, skinny, tall S, and it looks something like this. It looks like you go up, oops, let's choose black to make sure that you can see it. You go up, down, and back up. And that's the integral sign, right? And then what we do right next to that is we put the thing that we want to find the antiderivative of. And so I don't know what it is yet, but I do know that I want maybe a function to find the antiderivative of. And that's okay notation, but in mathematics what we like to do is also make sure that we're all very aware exactly what the variable is. And for us, we know that the variable here is x. And so what we do is we include this little punctuation here at the end to tell us what the variable is. We need to say that it's x. So we put this what's called a little differential. It's called a dx. We write it right here. We are dx. Okay. This is complete notation that says find the antiderivative of this function f of x, whatever it is. And you would write here whatever the function f of x is, if it's x squared plus 2 or e to the x or something, you would put that right there. So this notation is complete as it's written. This says find the antiderivative of f of x, and this little dx right here is simply telling us that x is the variable, and that's again shown by this notation. But if you have a function written here, you might not know that. So since this here asks us to find the antiderivative, well, we know notation for the antiderivative. We write that as capital F, or we can write it as capital F. So we can actually say that this instruction here, this integral of f of x dx, and that's how we read that, integral of f of x dx, we can say that that's equal to our notation for the antiderivative itself, capital F. Right? Because this instruction of the integral is saying find the antiderivative of little f. Well, we know that we call that capital F, so why don't we just say that those two things are the same? They mean the same thing, the antiderivative, and this says do find the antiderivative. Now remember that when we find the antiderivative, we're always allowed to put some sort of plus real number here, right? And so we can include that here also in our notation. And this is a complete statement using all the notation for our original function we're starting with, the instructions to find its antiderivative, and how we usually name the antiderivative, and the unknown real number that you're allowed to add. And some of these pieces of this statement have important names that we might want to sort of notice here, right? So I've already talked to you about this little symbol right here, but this is called, again, the integral sign. And the function that's actually sitting in here, right, the expression like x squared plus 1 or e to the x or whatever it would be, that's actually called the integrand. Okay? And the big plus c that we have over here is given also a special name. It's called the constant of integration. Okay? So again, this is an important relationship, and remember that this relationship is all dependent upon a derivative, right? Capital F is the antiderivative of little f, and that's what the integral sign is telling us to do, is to find the antiderivative of little f. But remember that the relationship between little f and big F is that if you take the derivative of big F, you get what? You get little f. Okay. And the notation again might be really confusing. It's a lot clearer when we start working with actual problems here, but it is important to understand all of the parts, right? And if I use these words integrand and integral sign, it's important for you to know which part of this I'm referring to. So let's try to use this notation here to try a problem. So let's try an example. Okay. So if I write something like, I don't know, we could try, how about we do one that we've done before, but we'll make use of our new fancy notation. So let's try e to the x. Okay, so that's my integral sign right there, a long skinny s. Okay, it's okay if mine's not very pretty. It's okay if yours doesn't look awesome. at first either. So this right here is asking me to find the antiderivative of the function e to the x. And notice the variable is shown to be x, right? So we know that x is the variable here. Well, we have to, again, think to ourselves, what is the function whose derivative is e to the x? Well, we know this one from our last video. The function whose derivative is e to the x is e to the x. So the antiderivative of e to the x is e to the x. But remember, we're allowed to have any plus real number we want here. Okay, so e to the x plus our constant of integration as we have up here, right? And again, remember the relationship is that the derivative of this right side here, the derivative of, this is capital F, the derivative of the right side should equal the function that's here in the integrand. Okay, I'll say that one more time. The derivative of the right side over here should equal the stuff in here inside. And that's a great way to check to see if you're finding the correct antiderivative, right? In order to check to see if you're right, you should take the derivative of this right-hand side and be sure that you get the function living inside the integral right there. Okay, let's try another one. So let's try another example. Let's see. Maybe we should try something like this. This one you may remember. We haven't done this one before, but let's see. So I'm asking for the antiderivative of 1 over x. So I'm asking for the function whose derivative is 1 over x. Well, if we think a little bit carefully, we might remember that there's something about a logarithm, right? So if you remember, the derivative of ln x, maybe we'll do a little recall down here. Sorry, that was yucky. The derivative of ln x is actually 1 over x. So what that means is if you start with 1 over x, its antiderivative is going to be the starting function, right? ln x. So when I'm up here, if it's asking me for the antiderivative using this integral notation, the antiderivative of 1 over x should be ln x. Okay, but are we all done? No, because ln x plus any number we want would also be something that would have the derivative of which is 1 over x. So ln x plus a constant of integration. Okay, and again, to check this, to be sure that we're right, all we would have to do would be to take the derivative of the right-hand side and be sure that we get the integrand. Be sure we get the function that we started with. So is it true, remember this is the notation for the derivative, that we can take the derivative of ln x plus a constant, and what is the derivative of that thing? The derivative of ln x is 1 over x, and the derivative of capital C is 0. So there's nothing, right? So this in fact does check, right? We get a check because the derivative of the right-hand side is in fact the integral. Okay. Now we need to be a little bit careful actually with ln x because something sort of a little bit funny happens. So notice, if you remember, that the domain of the logarithm function is a little bit picky, right? The domain of the natural logarithm is only positive values, right? So we'll do another little recall down here. Okay, so the domain of ln x is x has to be positive, right? And that's important because we don't know anything about this x. It could be positive, it could be negative. We know it can't be 0, so that's good to satisfy our domain of this guy over here, right? But we don't know if this x is positive or negative, right? It could be negative, and that would be bad for this because these two x's are the same thing, right? They mean the same thing. They're the same variable. So if this x is negative, that means that one could be negative, and we don't want that to happen, right? So what we have to do is be sure that there's only positive numbers getting plugged into this natural logarithm here, that this x is always positive. So what we do to ensure that, and this is going to be a little bit weird, is to say that the antiderivative of 1 over x here is ln x but with a little bit something else, right? So what we do is we say the antiderivative of 1 over x is ln absolute value x, right? Those absolute value bars, they're vertical bars. My first one came out a little crooked, but it should be straight up and down, straight up and down. Oops, now the second one's crooked. There we go, that's better. So the antiderivative of 1 over x is ln absolute value of x. That ensures that whatever goes into ln here is always a positive number. Okay, and that should be one of those general antiderivative rules that you should probably remember. All right, so maybe one more thing is to think about powers of x, and that'll be our last thing for this video. So we've got 2 pages here. We'll go to our next page. There we go. Okay, so we should think about how we can figure out antiderivatives of powers of x, right? So recall that we have the power rule. And the power rule, remember, allows us to take the derivative of powers of x, right? And if you remember, this says to do what? Bring that number out in front and multiply and subtract 1 from the current power. Well, if we started out with something like this on the right hand side, or maybe any power of x, let's just say we started out with a power of x, and we wanted to find its antiderivative, meaning we wanted to work backwards, right? We would have to reverse the process that we just applied when we did derivatives. So notice here when we did the derivative, we did multiplication and subtraction, right? Multiplication first and then subtraction. So to reverse that, instead of doing multiply, subtract, we will reverse that and do what? Add and then divide, because remember, subtraction is the opposite of addition, division is the opposite of multiplication. Okay, so in order to reverse the power rule, what we have to do is add 1 to the power and then multiply, or divide, sorry. Add 1 to the power and then divide, because we have to reverse the multiplication by using division. So how would I write that as a rule, right? So let's write a rule. So let's reverse the power rule. And if I'm going to reverse it, remember that means I'm going to be doing an antiderivative. So I can use the integral notation for that. So if I want to find the antiderivative of some power of x, and x is the variable, remember that's what that's for, saying x is the variable, okay, then what that means is that I can start out with what I have, that x, and now I need to reverse what I did. I need to add and then divide. So add 1 to the power, right, and then divide by that new power. Okay, so again, if I start with x to the 5th, I'm going to write x to the 6th divided by 6, and we'll do an example of that in just maybe a minute. So again, that's not quite done though, because we could have any real number included, right? So that could be a 5 or 5,000, it doesn't matter, just some real number here. Okay, and again, to check this, just to be sure that this does in fact work, to check that this is the right antiderivative, you could take the derivative of this right side and you will get x to the n, and you should do that on your own, right? Take the derivative of this right side, you'll apply power rule to this, right? Bring that n plus 1 out to the front, those will cancel, and you'll be left with an n, and the derivative of c is 0, so you'll end up getting this x to the n. Okay, now this rule is, this is a rule, right, and it's allowed to be used anytime, except for one important time, right? And you can figure out that one important time by looking at this denominator here, right? And this denominator will equal 0 if n is equal to -1, right? Okay, so we're not allowed to use this rule if n is -1, right? So if you get x to the -1 and you want its antiderivative, you can't use this rule, right? Because you'll be dividing by 0. That's bad. And we shouldn't use this rule anyway, because what would it look like if n was -1? You would have this, right? X to the -1. Right? Well, what is x to the -1? It's 1 over x. And we just talked about that a second ago, right? The antiderivative of 1 over x is, from the previous page, right? ln absolute value of x plus c, right? Okay, so we can't do reversing the power rule if you have the -1 power on x, right? We can't do that. We have to make use of the natural logarithm. Okay, so next time in our next video, we'll talk about properties and do some more examples.